Okay, so if you recall, last class, we started discussing about informed search. Okay, so under informed search, we discussed greedy, greedy best first search first. So for greedy best first, just use heuristic. Okay, and then we discuss it has some disadvantage if you just use heuristic. So a better one improvement is the A star search algorithm. So for A star search algorithm, it's not just use heuristic, it also considers the cost, the actual cost. So the evaluation function is the sum of the actual cost plus the heuristic. So this is informed search. So informed, why we call it informed? It's a kind of give you some information about the goal state. So compare with uninformed search. Uninformed, so you have no idea about goal state. So think about like breadth first search, depth first search, iterative deepening search, uniform cost search, digester algorithm, of those, you have no idea about goal state. But for inform, like greedy best first and A star, the heuristic tells you about some information about the goal state. So you use heuristic. So that's why we call it informed search. Okay, so be careful about this two, informed search and uninformed search. So for informed search, and if you recall, we also discussed like a tree search or graph search. Is it? So if it is tree search, and whenever we discuss the search algorithm, you recall, we needed to discuss its completeness and its optimal or not, its optimality, and time complexity and space complexity. So what is completeness? Completeness is if there is a solution and it can find the solution. So that means that a search algorithm is complete. So what is optimal? So if there is a solution and you can find what the least cost one, then it's called optimality, optimal. The algorithm is optimal. So here regarding A star, so the optimality. So what's the condition for its optimality? Optimality means find the least cost one. Optimality, least cost. Okay. So here it says A star is optimal if heuristic is admissible. So who still remember what's the definition for admissible? Admissible is the heuristic should be less than the actual cost. Is it? So heuristic needs to less than the actual cost. You remember about that graph from Arad to Berest? You remember that? What we use for heuristic, we use straight line distance. Definitely straight line distance between any two city is going to be less or equal than the actual route distance. Is it? So for tree search, you can guarantee the heuristic is optimal if it is admissible. You remember then regarding graph search, we cannot avoid the cycle, is it? So then A star, if you say just the heuristic is admissible, A star is optimal, and we prove that's not 100% correct. So then in this case, the heuristic must be consistent, or we call it monotonic. And what is the consistent? So there is a difference between consistent and admissible. Consistent is what? Is a node's heuristic. A node's heuristic must be less or equal than what? The actual cost between the node to its successor plus its successor's heuristic. So that we are guaranteed is consistent. So here is a different point. Okay. So consistent only function monotonic heuristic. Then it must go is heuristic and no heuristic must be less or equal actual cost. Plus what? So C is so you must guarantee this all this time. Here this is just admissible. But definitely, like here, that consistent, then it implies admissible. Okay. And so in general, it says most nature admissible heuristic tend to be consistent. And here we also said there is, especially if they come from relaxed problem. So relaxed problem, relax, by the definition is it take away some constraints for the search. Takes away some constraints for the search. Okay, so let's take a look. And it says A star is optimally efficient. So no other tree bases that use the same heuristic can expand fewer nodes and still be guaranteed to find the optimal solution. Okay, so here it gives us more idea about the A star. So then we come back to discuss the completeness, optimality, time complexity, space complexity. So complete, yes, is it? And optimal, it's also yes. Time complexity, then it's less than that Z star. And the space, it's exponential. Okay, and the next, let's see. The designing heuristic function. So this is the hard part, because once you find the heuristic function, it helps a lot. So this is a very hard part to find the heuristic function. So what will be the heuristic for the 8 puzzle game, is it? And here it has 2 heuristics. H1 heuristic, the first heuristic is what? Is number of misplaced tiles. So for this case, for the start state, so this is not like the route search, but you can still apply search algorithm. Okay. So in this case, the start state, number of misplaced tiles is what? Is 8. So that's why it's H1 star is 8. And H2 star, what is H2? So H2 star is total Manhattan distance. So Manhattan distance is number of square from desired location of each tile. So you can calculate. Is it Manhattan distance? So So one, did you say like one? This is the both state. Okay. And one is this way is supposed to be one. That's not. That has to be so this is regarding eight puzzle. Then it asks, are H1 and H2 admissible? Yes. And the heuristic says relaxed problems. So what is relaxed? It's a problem with fewer restriction on the action. That's called relaxed problem. So then the cost of an optimal solution to a relaxed problem is an admissible heuristic for the original problem. So definitely, okay. So in this case, it's if the rule of the eight puzzle relaxed, then that means a tile can move anywhere. Then H1N definitely will give the shortest solution. So same thing for H2. If you relax, if you take away some restriction so that a tile can move to any adjacent squares, not necessarily just Manhattan. Okay, anyway, so diagonal it can also, then says H2N will also give the shortest one. So further discussion about heuristic from sub-problems. So here says we can, for the eight puzzle, we can also give the H3N. So H3 is the cost of getting a subset of tiles into their correct positions. And in this case, because you kind of decompose the original problem into some sub-problems, so you can pre-compute and see the exact solution for sub-problem instance. Then you can build a pattern database. Then it can help you further solve the original problem. Okay, so it just provides us like different ways here. And then the next, so here just some terms. Oh, let's get back. So dominance in the heuristic discussion. It says if both H1 and H2 are both admissible heuristic, but H2 greater or equal than H1 for all nodes. Okay, then it says H2 dominates H1. And then it says which one is better? It is A star expand every node with the cost function less than C star, or the heuristic less than the C star minus that is the cost. So this says A star search with H1 will expand more nodes. And here just give us more discussion, okay, for the eight puzzle. And we can see it will expand a lot of nodes. And combining heuristic, if we have a collection of admissible heuristic, none of them dominates the other. How do we then is that you just find the largest one, okay. And another idea is regarding a weighted A star search. So this can speed up the search, but it will at the expense of optimality. Okay. So what it does is it takes the admissible heuristic, it's kind of inflated by a multiple alpha greater than 1. That you perform the A star search as usual. And then in this case, it's fewer nodes will be expanded. But the resulting solution may be suboptimal. So it may not be the least cost one. Okay, it may not be the least. But you are not going to expand too many nodes. because if we just use A star, we may expand a lot of nodes as discussed previously. Okay, so the next we can ignore. Okay, so here it gave us all search strategy comparison. Okay, and if you recall previously, I already said. Deepening search and the use of control. Those are informed or uninformed. Those are uninformed. So in uninformed search means those states, maybe you don't know those states. No in those states. So this is for uninformed. Never consider anything part of those. It is surely based upon the current node and then to its neighbor. It depends on breadth then will go level by level. If it is depth first, it will go like 2, 3, 4. It will pick the least cost and keep going. Remember like that, depth first. And if it is digester, then it will update based on all the from here, the explore the nodes to have the least cost. So anyway, those are so never consider goal. So this is a node. Here is goal. But it will never consider goal. So that's why we call it uninformed search. And we already discussed it. So for search, normally we also discuss completeness. Completeness is what? Guarantee you can find the solution. And optimal can lead to cost. This and then time, complexity, and space. And then we discuss these two. So these two are informed search. So informed research is what? You know the information, know some kind of information on those things. So basically is what? Here we have in history. So basically we have evaluation function. And here we don't have no evaluation. So here we have evaluation. So what's regarding the information that we know is reducing risk. Is it reducing risk? And when we consider heuristic, they don't need to remember monotonic heuristic or this is consistent. Consistent. This normally we are guaranteed. Correct. A star correct. So optimality. Consistent. Okay. For admissible. It's team-based. A star search optimal. Then that's fine. Okay, so these are just general idea. So greedy, is it complete? Is no. Optimal is no. Time complexity, worst case, is order of B to M. B is the number of branch. M is the depth of the least cost path. And for A star, it is yes for complete. Optimal, yes. But we said if heuristic is admissible, okay. Time complexity, then it's based on number of nodes. And here's a note on complexity of the search. The worst complexity of search is exponential in the length of the solution path. Exponential in the length of the solution path, but here be careful. The length of solution path can also be exponential regarding the number of objects in the problem. Okay, so we can see it can grow huge. Okay, so that's very interesting. Here it gives us an example. Okay, so that's about this basically heuristic. Okay, and then let's discuss the next. This is oh yeah, we need to go to new chapter. Let us stop this one. And oh, I need to share search. So we will move to chapter 5. So all the previous discussion is about chapter 3. So chapter 5 is regarding games and adversary search. So what is that? And just think about all the previous search. Uninformed search, informed search. When we discuss it, how many agents is involved? How many agents are involved? When we discuss all those search algorithm, how many agents are involved? Just one agent. Is it? So let's see. Here, why we consider games? Okay. As a game are traditional hallmark of intelligence. Yeah, we know. And easy to formalize. Also game good model of real world competitive or cooperative activities. Is it? So it's quite helpful. And types of game and game environment. So previously we also discussed this question when we discuss agent, the agent environments. So we discuss deterministic and versus stochastic. So stochastic normally it involves some randomness. So here, and also, is it the environment fully observable or just partially observable? So perfect information or imperfect information. So deterministic, so for deterministic, so here we have some games. Oh, I forgot. So for deterministic, so here give us some game example like chess, checkers, Go. For stochastic, backgammon, Monopoly. And why? Because it involved random. Okay, you may use a die, is it? And for chess, there is no die. Is it just two components? Your move or your opponent's move. And the same thing for battleship versus poker or bridge. Okay, so this is just some general game environment. And here, there is an important concept regarding alternating two-player games. But here, there is an important kind, it's called zero-sum games. So what is the zero-sum games definition? So two-player is player taking turn. Is it I move my turn and next your turn, and then my turn and then your turn. So that's alternating. And each game outcome, or here when we discuss in AI, we say terminal state. It has some utility for each player. It's your score kind of. Is it the simple case is you win or lose? Is it like you can see 1 for win and 0 for lose? So you have some score. Then here is why we say zero sum. It's the sum of both players' utility is always a constant. It's never going to change. It's always a constant. So here is a concept. Okay. And so, like I just said, previous the chapter 3 search we discussed, it's single agent search. Single agent. And for single, because there is no opponent involved, is it? So it's just the environment information, you know or not. Okay, so it's informed or uninformed. And here, when we see the alternated two-player games, this is different. So here, because you don't know what your opponent will do. So the solution is not a fixed sequence of action from start state to go state here. So this is purely different. Just think about all we previously discussed. Is it the least cost will be unique one. So that's why we say it's a fixed sequence of action. You got to follow that least cost. And your goal is also to find the least cost from start to go state. But when you play games with opponents, what's important is strategy or policy. So different strategy, different policy. If you draw a diagram, it's going to be different. Is it? So that's why it's not a fixed sequence of actions. And in our previous discussion for the single agent search, what is important to us? It's you find the optimal solution. You find the least cost one. And here, what is critical is efficiency is critical. Is it? What's efficient? Time to make a move is limited. Branching factor, search depth, and number of terminal configuration are huge. Okay, so that's why we say efficiency then in this case is critical. You don't want the game to take forever. That. And here it gives us why we say branching, search depth, and the number of configuration are huge. Here gives an example in chess. Is a branching factor can go to 35. Depth can go to 100. The search tree will involve how many nodes? 10 to the 154 nodes. Think about how large it says. Number of atoms in the observable universe is what? Is 10 to the 80. So it's even more than all of the atoms in our universe. Okay. So just think, is that computable? That is going to be very hard. Okay. And it says, so it rules out searching all the way to the end of the game. Is it? If every game you do like this, it's kind of unsolvable in this regard. And here to give it just like a tic-tac-toe. Okay, tic-tac-toe, the game tree, just think about how complicated it is. So tic-tac, you have two players. Suppose you call it max and minimum. Okay, max is a player, min is another player. Okay, and if max, so max can go to any of the 9 gray, any of the 9. And with max go to any of the 9, the minimum will have another 8 option. Is it? Another 8. And under it, then max will go. So just think about how big this search tree will be. This game tree will grow. Is it? So it's huge. And here it gives more abstract about the game tree. So here we just discuss 2 player, max and min, minimum. Okay, so max, we use this triangle, and min, we use the state it is. Okay, the state it is. So min, we use the inverse triangle. So here, so this is a very simple case because the depth is just 2 steps. Okay, so this is the terminal. So leaf node is terminal. And what here it shows, the number is the utility for max. So terminal utility for max. Okay, terminal. And the edge of the edge shows is what? Is the action you take. Okay, action. So here is the action max take. And this is the action that min take. Then it will lead to another state. Okay. And here there's another important concept we will say it's called minimax value of a node. Okay, minimax value of the node. So the utility for max of being in the corresponding state, assuming perfect play on both sides. So what is this minimax strategy? So then it will choose the move that gives the best, worst case of payoff. Okay, so what the idea is. So here just think about. So this just assuming, okay, because just think about, so you know a game, okay, and you design, if I do move this step, what opponent will move, and what should I do next? Until like the goal state, there are many possibilities. Is it? With so many possibilities, each possibility, the terminal state will have some utility. So here it gave us the utility. So if you are the max player, you start to move, then you will think, what I'm going to do. Is it? So how do you calculate? Okay, you assuming the terminal state you are already at. Is it? So, but here just think about, you think and your opponent will also think about what's going to be benefit me the most. If you take step, what I'm going to take. Is it? So here, this game search tree, then what we are going to do is we are going to do back propagation from leaf node all the way to the root node. Okay, so then just think about, in this case, what is the minimum we'll choose? The minimum based on this, we definitely will choose the minimum number, minimum value, so 3. Is it? And for the second branch, what value it will take? It will take the minimum value. So that's why it is 2. For the third branch, what it will take? It will take 2, the minimum value. And then for max term, what it will take? Definitely it will take the maximum value among all this action. So it will take 3. So that's how you come up. Assuming this is some very simple one, then you design like this, then you will know what your utility you will get. Okay, so you can see max didn't get the largest 14. Is it? And minimum also didn't get like it's what it wants, like 2. Is it? So because it's opponent, so you need to calculate what's going to based on your opponent's strategy. When you move, then your opponent will also do the optimal calculation for himself. Is it? So this is the concept of minimax value of a node. Okay. It says utility of being in the corresponding, assuming perfect play on both sides. So both will make the perfect move. Okay. So minimax, the value, how do you find the value? So it is utility if node is terminal. So the maximum, so will be what? Will take from the successor. Among the successor, it finds the largest value. And for minimum, then it will find the minimum utility value from its success. Okay, so that's how the two opponents to pick up the value. Okay, pick up the move. Okay, then let's see the optimality of minimax. So it's a minimax is optimal against an opponent, an optimal opponent. Is it because each one will either pick the maximum value or the minimum value? Then you may ask if the opponent is suboptimal, it doesn't move with the optimal, but you will see your utility can only be higher. Is it? Then if you were playing an optimal opponent. So even though your opponent may not make the best move, but for you, you still make the best move. Is it? Yeah. So it's a different strategy may work better for a suboptimal opponent, but it will necessarily be worse against the optimal opponent. And then so definitely this minimax will make the best if you always take the optimal move. That's what it means. Even though the opponent may make the suboptimal move. Okay, and here, if there are more than 2 players, then what should we do? Like in this case, there are 3 players, red, green, and blue. 3 players. For 3 players, then each one will have the utility value. Is it? Then in this minimax, then we will not work. So then in this case, each opponent, each player will maximize their own utility at their node. So they will always pick what's the benefit, what's the most benefit to the to itself. So you always stick with this rule. Then you won't lose. That's what it means. So everyone just pick what's the best for you. Is it like this blue? Then you just pick the best because between 3 and 2. What's the best for me is this one. And for this, what's the best is between 1 and 4. So that's why it pick 7, 4, 1. And what's the next is between 1 and 5. Which one is larger is 1, 5, 2. That's why it pick that tuple. And what's this one the best compared with 7 and 4? So 7 is a large. That's why it picked the large. So each one will only pick the benefit you benefit the most. You don't care about the other. Okay, you just, okay, what's the most benefit to me? Okay. And here it shows more like for green. And the green then compare with 2 and 1. So that's why it's go with the 2. And among these two, 1, 5, 2 and 7, 7, 1, it should go with 7, 7, 1. Because, it should go 1, 5, 2 because 2 is larger. Yeah. And then for red, it will just compare 4 and 1. So definitely go with 4. So that's just more general. Okay. And what's next is going to discussing is about alpha beta pruning. And we just see the mini-max game tree. It's going to be huge. You remember it can be like more nodes than of the atoms in the universe can grow to that huge. Is it so? Here it says, is it possible to compute the exact minimax decision, but we don't expand every node in the game tree? Yeah. So is there some way we don't expand all of the nodes? Yeah, the answer is yes. So let's take a look at this example. So here we have this minimax. So terminal, you have this 3 value, 3, 12, 8. And for mini, so it will take the minimum value. Minimum is 3. And because it's 3 at this point for max, what it will take its value. At this point, you don't think about other brand. Then currently it should be 3. Is it? Because it will go with the value can only be greater or equal than 3. Okay, so you are going temporarily the largest value for you if we write a program, and then you update your current largest is 3. If they think about when we write a program, the current value, when you do find the maximum, it updated to 3. Is it? Because initially you set it to what? Negative infinity when you write a program. To find the minimum, you set it to positive infinity. If any value less than, you update. And for this, if anyone greater than negative, you update. So we update. Is it 2, 3? And then let's take a look here. So here is a trick. Is it? Just think about it. No, there's only 2. They're only update. If the value is great. No, we will find the and the first rank, the first is success. It has the so this 2 is less than that one is and then but what's interesting is any value great. And what if it is any value less, any value less, any value greater than 50%, any, no. Then just think about it. Here, does this no dispute on this? Is it the only other branch? Not in the center. And then because what is shared in any value three? The first value is already less than 3. Is there a need to think about this branch? So you can. So that's why we call pruning. That's the idea. So you can prune this branch. Okay, we can prune this branch. And then next, let's see. So for this one, 14, can we prune? No. Is it? Because the current is, okay, it's less than 14. But 14 is greater than 3, so we cannot prune it. Then it says, okay, it's 5. Can we prune? No, it's still greater. Okay, the last one is 2. So for this branch, we cannot prune. Okay, so here gives us some very basic idea, okay, about pruning. So then here it comes the idea about alpha beta pruning. Okay, what is alpha beta pruning? So with alpha beta pruning, we have alpha pruning and we also have beta pruning. So let's see. So here is the alpha is the value of the best choice for max. So far at this point, just like that 3, so far we found. At any choice point above node n. Okay, so anyway, so that's why we make it as alpha. Okay, for this max node. And we want to compute because after the successor of max should be minimum. This should be min. So we want to compute the minimum value at node n. So this node n. Okay. Therefore, then you remember we node n has a branch. So you're going to do a loop with each one. So when you do the loop, it says if it drops below alpha, will max ever choose n, as we just saw? No. Is it? We are not going. So it says we can ignore n's remaining nodes. Is it? We can ignore n's remaining nodes. So this is called what? So you did the alpha pruning. Okay, and similar for beta. Beta is minimum. Okay, similar, such similar idea. And see, so here it gives us the alpha beta pruning algorithm, the code, the pseudo code. And here when we discuss alpha and we also discuss beta pruning. Okay, so let's see. So here we do alpha beta search. Alpha beta search, so here we want to find the minimum value. Okay, minimum value is what? It's many nodes need to make a decision. Minimum value. So alpha is what? Alpha is best alternative available to max. beta is best alternative available to mini. So let's see what this mini value function works. So it has nodes and alpha and beta value. So if it is already at the terminal state, then you just return. Is it? And because you're going to find the mini, so that's why the initial value is going to set as infinity, positive infinity. And then for each action from the node, you are going to compare the minimum value and the maximum value among the successors. The maximum value among the successors here. Okay. And it says if this value less than alpha, then you return. Is it? Then you return. Otherwise, you can update the beta value. Okay, so basically, this is what? This is, we call it beta pruning. Okay, beta pruning. And similar for the max. So similar concept, we are not going to go over it. We will take a look at example to have better idea. And general some idea about alpha beta pruning, will it impact the final result? It will not. And but we can also see the amount of pruning depends on what? So move ordering is very important. Is it? Move ordering. And so normally we should start with the best move. So what's the best? It's highest value for max or lowest value for min. And here to give us some idea like chess, what you can try. Some strategies that capture first, then threats, then forward move, then backward move. You can also try to remember killer moves from other branches of the tree. It says with perfect ordering, time to find the best move can be reduced to order of, so B is the branch, number of branch. M is the optimal path length. So you can cut almost half, 2 to the half. Okay, so that's a lot. So depth of search is effectively double. So here it gives us an example about alpha beta pruning. And this is a very good example because it involves multiple levels. Okay, so let's take a look. So when we analyze alpha beta pruning, we start at the terminal state. Okay, start at terminal state. So this is a minimum. So its parent node will be the max. So between these two, definitely 3. Is it 3? Okay, and for this 3, then its parent is what? It's going to pick minimum value. So that's why here beta value at this point is 3. Is it? Beta value is 3. You can set it as 3. And then let's see this branch. So here it's find the maximum value. So its leftmost value is 5. 5 is greater than its beta value. So is it possible that you will go to this branch anymore? You will not. Is it because B's value, B's alpha will be greater than this beta? And the beta just find the minimum between these two. Is it? Beta will only find the minimum between these two. So that's why this branch will be beta pruned. This makes sense? This makes sense? Yeah, okay. And okay, now we fix this branch. We can set C's alpha value. Be careful, okay, you got to get this node completely taken care. Then you can propagate the alpha or beta value. Otherwise, you cannot. You need to take care of all of the branch for that node. Then you can set up its alpha or beta value. So at this point, C's alpha value is what? Is 3. Okay, so this whole branch we already taken care of. So then let's go to C, second branch. Okay, so node D, then we move down to node O. Node O only has one branch, so it's 0. It's 0, the max is 0. Okay, max is 0. So the beta value at this point is 0. Okay, beta value at this point is 0. And then let's see this branch. And here you assume all of the value is going to be greater than 0. Okay, don't include the negative value. Oh, it doesn't matter. Okay, so let's see. Because this beta is 0 here, and this beta is 0, and C's alpha is 3. This, because this is minimum, and its leftmost is 0. No matter what its other branch value is, it will be what? And over here, you care about maximum. And this alpha is already greater than the current beta value. So is it possible that it will grow more? No. So do you still need to consider for node C about this branch? No. So that's why node D can do what? We call it alpha branch or alpha pruning. So then node D is at its alpha prune. Okay, alpha prune. Then let's go to, so basically you see this branch is pruned. And here you also prune a branch. And then let's see the last branch. The last branch, you go all the way down here. So here's maximum, so it's 2. So beta at this point is 2. Because the beta is 2, the right branch's value, no matter it's what, it's going to be less than 2. And does C need to worry about all of the others? No, because C cares about a value greater than 3. So does C care about E anymore? No. So C doesn't care about E anymore. So C will do what? Will do alpha pruning. Okay, so node E is alpha pruned by C. Okay, so here you see this branch, and this branch are all pruned. So you save a lot of expanding node actions. Okay, you can save a lot of search space because those are unnecessary. So this we call alpha beta pruning, okay? And it says even with alpha beta pruning, in reality, the search space is still quite a lot. Okay, so normally you remember when we discuss the uninformed search, we discussed the depth first search. So a way to avoid, because depth first search may not give you optimal paths, is it? So a way to solve that, we use what? Iterative deepening search. Is it? So here it's kind of some idea like that is we can cut off search at certain depths and compute the value of an evaluation for a state instead of its min-maximum value. So the evaluation function here, so for a state, so here it's kind of, we kind of borrow the heuristic concept. Okay, you use some evaluation function. So evaluation function can be thought of as some probability of winning from the given state or expected value of that state. That's what here it says. The common is that common evaluation function is a weighted sum of features. And here's give us an example. It's called a weighted sum of features. Okay, so the W value here is material value of a piece for chess. And the F is advantage in terms of that piece. So you can use this kind of information. And how do we find the evaluation function? Is that you may be learned from game database or having the game play many games against itself. Okay, so this is you try to use some evaluation function. Okay, so I think this concept is kind of, it's not heuristic. Okay, it's not, but it's kind of, you try to borrow it. And do the cutoff search. It says a horizon effect. So you may incorrectly estimate the value of a state by overlooking an event that is beyond the depth limit. So when we do that cutoff, is it, so your estimation may overlook something. That's very possible. Is it? So for example, it's a damage move by the opponent that can be delayed but not avoided. And the possible remedy is that we can do a quiescence search. Okay, the quiescence do not cut off search at positions that are unstable. So when you do cutoff, you need to pick some place that is stable. And we can also do singular extension. Singular means you make some strong move that should be tried when the normal depth limit is reached. Okay. So here just some other techniques, okay, to discuss about to not expand your search space too much. But anyway, this is a trade-off. That if you don't want to expand the space, you will face the issue that is not stable. Okay, you can. It's hard to avoid, but you can do some bad. So that's why with this it's a possibility. Okay, just later on when we do machine learning, we will also say it involves a lot of possibility. Okay, it's purely based on possibility. Other advanced techniques is that we can do the transposition table to store previously expanded states. You can do forward pruning to avoid considering all possible moves. You can also do lookup table. Okay, so here it just gives us some other advanced technologies. And chess playing system. So this just some extra information. It's a baseline system is 200 million node evaluation per move. Just think about it. Okay, so even after we add alpha beta pruning, 10 player, okay, it's experienced player, okay, and the deep blue, what it says is 30 billion evaluations per move. Singular extension evaluation function involves 8,000 features. Large database. So this is for deep blue. Okay. So anyway, this is just some extra information. Okay. And I think we not this. And I think we are done with the with this chapter, chapter 5. Okay, so chapter 5 is mostly discussing about games and adversary games. So it involves multiple agents, not like the chapter 3 discussion, the search. It's only involve one agent. Okay, so that's all the information. So, part of the homework you can start with because the homework also has one okay, that's all the information. And for all of you who are late,